This conference will now be recorded.
Good morning, and we're going to talk a little bit about a few subjects today regarding how we can positively affect the use of VFDs in the water industry. And this isn't going to be a sales competitive thing. To be perfectly honest with you, there are a lot of drives out there that will do the job. And as engineers, we try to focus on things that can differentiate our contribution. Deciding whether we're going to use an ABB drive or a Yaskawa drive or a Danfoss drive or a Siemens drive or what have you, I'm not so sure that effort is addressing the point of improving the performance of the VFD in this application as much as addressing some other things. The VFDs in my career, which has spanned quite a number of years, have come up to the point where there are many companies that meet the bar of performance for the water pumping application. And that is as it should be, because the transistorized pulse width modulated VFD has been around for since 1983 in this country. So we'll focus on a few other things. Now, there are two things I'm going to address before that. One, a comment. As I've said before, the matrix technology is a sea change in addressing the VFD in the water industry, and that has significant benefits directly to the application. And soon you will see matrix drives from all the major brands. The other thing I'm going to do before I get into the meat of this class is to do a quick review on one of the older technologies that enhances VFD performance in the water, wastewater, agricultural market. And we've talked about this before in that addressing the issue of harmonic distortion, one of the key negative impacts that using a transistorized diode front-end drive has in the water application, the detrimental effect that it has on the power quality, and what the power companies are doing about it, what we can do about it. One of the traditional technologies is 18 pulse, and it is a static filter approach using the standard diode front-end VFD, perhaps enhanced because we have to add diode bridges to the front end of the VFD. And the reason I want to go over this briefly today is because I've had a couple of inquiries regarding the 18 pulse designs, a lot of which are being retrofitted out now. When the VFD needs to be replaced, typically the filters are still serviceable. Those big transformers last quite a while. They are passive, and therefore if you keep the voltage spikes down and maintain the thermal environment, your transformer is going to last probably longer than the drive. But there is some confusion out there because there have been a couple of different competing technologies that have ended up in the installed base, and as a result, some of the people going out to retrofit or replace drives have really stepped in the old gopher hole, shall we say. So I want to go on record with this little bit of technology to help people avoid that gopher hole. So I'm going to share the screen, and you'll see a variety of little diagrams up here. Now, we'll start with the 12 pulse. That's not very big, is it? I hope you can see that. Oh, wait a minute. Okay, that's the best I can do in terms of size versus focus. Bear in mind that the standard drive is 6 poles, 6 diodes, 3-phase line in to a DC bus on the output of the diodes. Full wave bridge rectifier. What you see here are 12 diodes, and you see 2 3-phase lines coming in from the main transformer. And actually, that's not the main transformer. That is the phase shifted transformer. And what you have here is a Y primary on this transformer and 2 secondary windings. And you can certainly do that in a transformer. It's quite easy. This isn't, as they say, rocket science. But the sine wave out of the Y secondary winding is shifted slightly from the delta secondary winding. So if you look at the 2 sine waves overlaying each other on an oscilloscope, for example, you will see that those 2 sine waves don't line up. The first sine wave starts, and about 15 degrees later in the cycle, the full cycle being 360, about 15 degrees later, maybe 10 degrees depending on the design, the second sine wave starts. So, phase shifting those, we'll explain the reason why we do that in a second, results in the fact that the voltages on this winding and the voltages on this winding don't correspond from a phase standpoint. They're out of phase. They're phase shifted. You dare not connect these 2 outputs. However, once we go through a full wave bridge rectifier, they can be connected on the DC side. Now, this is a 12-pulse bridge rectifier that has the diodes in series. This is to be differentiated from the diodes in parallel, where each diode bridge feeds across the full DC bus. And I'll show you how that works in a second. Let me get to a I'll use this one. This is an 18 pulse. Zoom it up a little bit. Now, let's just drop this last diode bridge to complete the discussion on the 12 pulse. Note that each of these diode bridges connects across the full DC bus. There's phase shifted secondary winding 1, there's phase shifted secondary winding 2. This is a diagram for 18 pulse, but we were talking about 12 pulse, so let's just ignore this for the moment. Notice that each of the diode bridges connects to the plus rail and to the minus rail, so they are in parallel. If we go back to the other diagram, you will see that those 2 diode bridges were in series. That's the main point that I'm trying to make here, because some manufacturers will use series diodes on the output of the phase shifted transformer. Some manufacturers will use paralleled diode bridges on the output of the phase shifted transformer. This can get you into a lot of trouble when you go to retrofit and your diode bridges are not configured properly. It'll end up costing you quite a lot of money if you discover it at the site. So here, for example, is an 18 pulsed seriesed diode bridge setup, where this is the negative rail of the DC bus, this is the positive rail of the DC bus. I hope you can see my cursor, and you can see that the diode bridges are in series across the full span of the DC bus. In this particular case, the designer selected a 20-degree phase shift between the outputs. Again, you cannot connect these three AC outputs of the overall 18 pulse transformer. Well, you can, but you'll do it once. The fact is that the voltages are different because the sine waves are shifted. You can obviously connect the DC bus once we rectify all that AC to DC. In this case, seriesed. In this case, paralleled. Now, by the way, this is roughly how your input current looks with an 18 pulse setup. And that is a picture of the 18 pulse system at rated load. We know that because it's a passive filter, it doesn't react to conditions, and as you change the load and change the speed, which on a centrifugal pump are coincident events, you will get less and less performance as you come off of the optimum design point for this passive filter. But the main point is parallel diodes versus series diodes, and you don't want to discover that at installation time. The implications are this. You would have to go internally into the drive and rewire your diode bridges, which may be physically possible. On big drives, you're going to be dealing with big conductors, possibly bus bars, but you're not going to be able to do it under UL 508, obviously, because you're in the field. So please be aware of that. I hope this allows you to avoid stepping in the gopher hole, if you will, when you go to retrofit some of these 18 pulse systems, many of which were installed in the 90s and early part of the century and are definitely coming to end of service life. I'm going to make a short comment on that. When we go to service and repair a drive that's been in the field for longer than its anticipated or designed service life, we have to make a decision. Are we really serving the best interest of the customer by repairing the part of the system that has failed? Or are we doing the customer a service to recommend replacement to state-of-the-art technology, giving him another 20-year run, if you will? And that's a decision that you have to make. I'm here to bring up the decisions. I'm not here to make them for you. This is an individual situation. It's up to the end customer ultimately. But the factors are significant. When you have a failure in a drive, for example, a failed diode, Yaskawa's procedures say you should replace the entire diode bridge. Often that's not done for reasons of economy. But even if you replace the failed diode bridge entirely, that diode failing after 20 years is giving you an indication that some of the other components in the drive are also reaching the end of their service life. The capacitors, the transistors on the output, the diodes on the output, several other power components, not to mention the circuit boards themselves. So you've really got to consider that in terms of the customer's best interest by evaluating it on something other than just a short-term cost. I have to make decisions like that in my own personal life when I go to repair cars. I tend to drive cars till the doors fall off. And that means that I have higher maintenance costs on the car, and eventually I have to make the decision that it's time to replace the car. This is the decision we face in this scenario. And with so many of the drives, especially the 18 pulse stuff from the 90s, coming to end of service life, these decisions need to be made intelligently. So, one more point before we move off of the 18 pulse discussion, and that is that there's another type of transformer that was used out there. These are the transformers here are isolated transformers between the primary and the secondary, and you have separate windings for the primary and, in this case, the three secondaries. There's a technology out there that was used primarily for cost reasons. I don't see a lot of technical advantages, but this is using an auto transformer, which, as you can see, does not have any galvanic isolation. This is completely incompatible with the galvanically isolated primaries and secondaries of a standard 18 pulse transformer, this or 12 pulse transformer. This happens to be a 12 pulse setup. You can do these auto transformer situations with an 18 pulse. The transformer is lower in cost because there's less active material, and I'm not here to argue much about the better or worse of it. I just want you to be aware of it, because when you go to retrofit and you are coming in expecting a standard 18 pulse or 12 pulse transformer, you end up looking at one of these. Again, you're going to be spending a lot of money to rectify that situation as the installer or as the engineer. This situation, this type of multi-pulse system was supplied primarily by Toshiba and Allen Bradley back in the day. And again, be aware of it. Make sure you do your homework up front. If you have any questions in terms of the 18 pulse system that you are facing when you go out to do a retrofit or to do service or upgrades, please feel free to contact myself or Craig Swift, and we will give you neutral technical advice on this. This is part of the benefit of being part of this community. So there you have it. That's what I wanted to say about the 18 pulse situation. Now let's move the discussion to how we can positively affect the water application and where we can focus time and investment to get maximum benefit. As I said in the beginning of this class, there are many VFDs that will do the job. And I think that wrangling between one brand and another, if I put my engineering hat on, is not good time spent. We can focus on other things, which we will elaborate on in a moment. Certainly, if I put my sales hat on, I would want you to use Yaskawa. But again, that's marginal benefit unless we're talking about the matrix drive, which is the sea change design technology. But let's say we're talking about a standard diode front end drive. The one thing that I will tell you about VFDs in general is that you need to treat them like you treat your stereo. And you don't throw your stereo out in the sandbox or next to the pool with all the chlorinated water, or out in the rain. So that implies that we can affect the situation positively and affect longer life for the drive and less downtime by addressing the thermal environment that we put the drive into. And that's an area that in our industry, unfortunately, we have a lot of variant performance, if you will, on that. Yes, one drive to another from the major brands, pretty much same performance on the water application than a centrifugal pump. Enclosure-wise, horrendous. I've seen all kinds of variation and some really excellent implementations and some really poor implementations. And I can look at the poor ones and say, yeah, that drive's not going to last much more than 4 years. So let's address thermal, and let's address water and dirt. So one of the finest applications that I have been involved with, and I will put up there as an example, is the application that was done in a project I had the honor of being involved with, as did Craig, and that was at the Rosedale Rio Bravo facility in Bakersfield. Because this is a technical class, I will say that large horsepower, any quality VFD enclosures can be applied using this. And this is a method of doing things that is not a lot of extra cost, but dramatically improves the quality of the environment for the drive. So we start with a whole bank of drives. These happen to be matrix drives, as you can see, but we can use this for standard drives as well. And you will see inlet and outlet vents on the front of these doors. Those are to provide airflow over the circuit boards and the thermal energy being exhausted from the upper port, because we always at Yaskawa put fans at the top, filters at the bottom, and suck air up through the system. The reason for that is that it follows the natural convection, so we're not fighting the natural convection. And we have lowered air inlet velocity at the inlet, so we don't suck up as much dust. We don't make a Hoover vacuum cleaner. The fans have to be sized up a little bit because they're blowing out hot air instead of blowing in cool air. But that's a small compromise to achieve higher performance of this design versus fans on the input. Again, we're balancing thermal environment with dirt environment, particulate ingress, and moisture ingress. In this controlled room, this is a concrete preformed building. We don't have a lot of issues with dirt and moisture, but we definitely have some thermal. So here's a principle to recognize in this discussion. The heatsink of the drive wastes off about 80% of the drive's watts loss. About 20% comes off of the circuit boards and doesn't go through the heatsink out to atmosphere, which is a convenient separation of watts losses for this particular application, because yes, I still need to have some airflow in the front of these drives in order to get rid of that 20%, but I can waste the 80% off of a heatsink, which means I can extend it out the back of the enclosure, keep it out of the electronics section, and indeed that's how we do most of our configured packages. The unique thing about this application is that the heatsink airflow, which is going up the back of the drive, so you can see the heatsink extended out here in this heat column, is not exhausting into the atmosphere of the building. These are standard NEMA 3R enclosures from Yaskawa. And the first question is, well, why are you using an outdoor duty enclosure in an indoor building that you spent all this money to build? Well, NEMA 3R, it turns out, doesn't cost that much more than NEMA 12. NEMA 12 being oil tight, dust tight, NEMA 3R being rainproof, and in the case of Yaskawa's implementation of NEMA 3R, it is also NEMA 12. So it's oil tight, dust tight, and it resists outdoor weather conditions such as rain. It's more equivalent to the ingress protection rating IP54. And I'm not going to go over ingress protection ratings now, just Google them and you'll see that those two numbers, the first one is particulate ingress, the second one is water. Did I say that right, Craig? Or is it water first, particulate ingress second? But it's one of those two, so Google it. At any rate, these are outdoor duty enclosures mounted inside an expensive concrete building. Why did we do that? We did that for thermal reasons. We do not want to exhaust the 80% of the heatsink watts losses, which are connected directly to the diodes and the switching transistors, into the building. Why? We were able to reduce the size of the building, and we reduced the air conditioning load in the building by 60%. Significant cost savings that have nothing to do with the drive, or do they? By punching a couple of holes in the building wall, and this is prefab, so we had to plan this out. We were able to draw outside air in, outside air. Why? Because this is an outdoor duty rated enclosure. We got these all over the Central Valley standing on concrete pads out in the full sun. So they can certainly be mounted inside a building and draw outside air in from the bottom and exhaust it out the top and avoid putting 80% of the watts losses of each VFD into the building and therefore onto the air conditioning load plan. The outdoor looks like this. Note we are on the north side of the building. That's logical. We also, in order to reduce a tremendous amount of dust being sucked up into the filters, even with the low air inlet velocity of having the fans at the top, there are the fans, we put gravel out here. None of these things that we've done are significantly expensive. Orienting the building doesn't change the building cost that much, if any. The gravel wasn't that expensive. The doors or the holes for the vents were not that expensive, as long as we gave them the right dimensions before they cast the walls. And these hoods are the standard hoods that come with the drive. The cost adder was to put these ducts in play. So we had a little bit of sheet metal cost. For that investment, we maintained the good environment that the drive is rated for. Certainly we've proven that in the agricultural world. And we reduced significantly the building cost. Here's the detail on the hoods. You can see in the bottom, those are our air inlets, and these are our forced air outlets at the top. And the north side of the building is a good place to put them. I guess it's also a good place to put the lavatory. Nobody wants to sit in a hot box. So that is one of the non-VFD brand related improvements that we are suggesting that the industry starts to consider in order to dramatically reduce the overall cost of the installation, which is certainly a nice motivation, but the main purpose is to ensure that we have good life on the drives. I will send this presentation out, and now when we talk about other things that we can do to increase reliability and to decrease or avoid excessive extra cost, perhaps a small investment to get a large return, certainly a good tactical plan in any design exercise. One of the other things that we can talk about is multiplexing. And multiplexing is a great tool to use when you want to increase your reliability. And what it involves is taking several drives and several pumps to basically achieve the same flow and pressure regulation. Now, that inherently makes sense. Do we drive the cost up? We do. If I have 4 200 horsepower drives versus one 800 horsepower drive, I have a single point failure on the 800 horsepower drive, but I have less real estate used, less wiring, less installation costs, and to be perfectly honest with you, the overall cost is less also. So why use multiplexing, and how do we judge the return on investment for the extra cost of the multiplex for 200 horsepower system versus the one 800 horsepower system? Bear in mind that we're also now using 4 200 horsepower pumps and the associated piping associated with that as well. So we're really talking about a bit of extra cost. Now, hang on one second while I try to navigate my other screen that you can't see to try to get the literature up that I want. I need an IQ diagram where I can show you the multi-pulse configuration. And I apologize for not doing this ahead of time. But I had too many things on my screen and I forgot. So one of the advantages of multi-pulse is that you actually have far better overall reliability. And that is because if a drive fails, it's not a single point failure, because you have other drives that can take its place. And while we're sizing for 800 horsepower, the reality of it is that our application is probably going to be running at something less than that. And therefore, if I lose one drive, I probably still have enough capacity to meet demand. And that allows me to withstand a drive failure without withstanding output reduction. Now, I'm sorry, this is embarrassing. I cannot find my IQ pump. That's ridiculous. That's it. There it is. Nope. I'll be darned. I can't find it. I must have deleted it by accident this morning when I was preparing for the class. So, Craig, do you have an IQ pump bulletin handy that shows a multiplex setup? I'm embarrassed to say that
I'm limited bandwidth at a hotel, so I don't know if I can show it.
Okay, that's all right. I will, as I'm talking, I'm going to go to Yaskawa.com and find one. Documents, core manuals, sales literature.
And then, I don't know if I'm breaking up, but the IP rating was, it's dust first, moisture second.
Thank you very much. So IP54, particulate ingress is the 5, and moisture ingress is the 4. So let's see what we've got here. Q family brochure. They changed all the brochures on me. It drives me nuts. Yeah, that's not what I wanted. Let's see if we show the multiplex system on this. Oh, there we go. Okay. Thank goodness. I swear sometimes these classes can be stressful this early in the morning. So this is a multiplex system. And what it involves is a lot of extra piping, a lot of extra hardware, a lot of extra wiring. But what you get is a remarkably reliable system. The multiplex system also gives you redundancy in the mechanically driven equipment, which is the pumps. So, in the case of, let's just take the 4 200s here and ignore this one, but you can do up to 8. In this case, we have an 800 horsepower sizing. We probably have an average load requirement of something between 500 and 600 horsepower, based on the fact that we wouldn't be putting variable frequency drives into this scenario if we weren't intending to vary the speed and therefore vary the output. Again, I will say that if your output requirement is steady, size a pump to run at full speed to handle it, and don't bother putting a drive in there because it's just going to cost you extra money and the drive won't give you any benefits. But in this case, we're going to assume 500 to 600 horsepower average load. We're sizing up to 800 horse. Now, the single 800 horsepower drive in this scenario is a single point failure. It goes down, you get no water. In the case of the multiplex system, if a drive fails, you get water, and you're probably still meeting your full demand. Even if 2 drives fail, you're still getting 400 horsepower worth of pumping capability, and that can get you through the situation till you can get the 3rd and then the 4th unit repaired. So you see the efficacy. How does the multiplex system work? Well, one drive is the master, and one drive receives the signal for pressure, and basically via the network tells the other drives what to do. This is a subnetwork that is peer-to-peer on the Yaskawa drives. It happens to be a Modbus RTU network. It's RS485, super reliable, and certainly fast enough for what we need to do in a multiplexing environment. You basically just connect to the R plus, R minus, S plus, S minus terminals. It's easy to wire up, and the programming is very simple. You just go in and you designate the drive's addresses. But in the multiplexing setup, and I'll show you the multiplexing setup cheat sheet in a minute, you don't need to set one as the master and leave it as the master. And why do we not want to do that? Well, that makes the system, again, a single point failure. So notice that the system properly has pressure sensors going to each of the drives. What this allows us to do is to designate any drive as the master. And in doing so, gives us maximum flexibility. So now we get an additional benefit coming out of this. We eliminate the single point failure of one of the master drive failing, because if the master drive fails in the multiplex system properly designed, and bear in mind this is not just Yaskawa, but anybody's multiplex system, then the second drive in line will assume command. And if that drive fails, the 3rd drive in line will assume command, etc. Because each drive has pressure feedback, it can be the master regulator, and it can call in the other drives as necessary. In the case of one drive failing, the remaining drives. So that's the added benefit. And then there's an additional benefit in that the master can be designated to change per schedule, not because of a failure, but just per schedule on any given day. So if this is Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, Monday, you can keep circulating the masters. What does that do? Well, it evens out all the wear on the pumps. Your wear rings won't fail prematurely on, well, they may fail prematurely for some other reason, but they're not going to fail because of wear, because we're evening out the runtime on all of the pumps as well. And that's a significant benefit towards obtaining maximum life of the system. So a multiplex system can cost you between 1.5 and 2 times the cost of a single drive, single pump system. And you're going to have to look at that investment and say, are my reliability requirements and my reduction of downtime over the next 10 years worth it? You certainly will get higher reliability and much reduced downtime with a multiplex system. So let's go and take a look at the, what is the multiplex cheat sheet? Oh, I accidentally closed it. Bear with me one second. I'm not exactly up to speed. I should have had more coffee this morning. There we go. This is the multiplex quick start procedure from Yaskawa. As you all know, we have a simplex quick start procedure. It's basically, in this case, 5 pages of very, very specific step-by-step illustrated methods to start the multiplex system and configure it the way you want. And similarly with the simplex procedure, the manual, of course, as you know, is the size of a New York telephone book, but unnecessary to get the system started in pressure regulation, whether you're simplex or multiplex. So, it's not going to cost you a lot of extra money to use the multiplex system from a technical and support standpoint, because the documentation is very good. Okay? Now, all the standard IQ features that you are used to will present themselves in the multiplex system as well as in a simplex system. And I will say that is similar to the other brands of multiplex versus simplex systems that I've seen out there on the marketplace. There's no reason to have a feature degradation, because remember, you have a master drive, and that master drive has all the features that you require for the water application. So, how else can we positively affect the water application through some differentiated, innovative engineering decisions? And we've addressed the environmental issue. We've eliminated air conditioning, which was sort of unspoken up until now. When you eliminate air conditioning in the water application, you eliminate another single point failure. And as a result, increased reliability. Why? Because you're sizing the drive to handle its environment on its own. You're not sizing it such that it needs a crutch. That's a very important design point. Air conditioning is a crutch, and it allows you to undersize your drive thermally. But when the air conditioner goes out, that undersized drive can't do the duty. One of the other things that I'll say in terms of affecting the design, affecting the performance positively with minimum return on investment, is in the use of inverter duty cable. This is another differentiating factor that will increase the cost of the cable by as much as 50%. So instead of spending $10 a foot, you may be spending $15. But the inverter duty cable has manifest benefits in terms of life of components, especially the motor, but also all of the instrumentation in the environment, because the inverter duty cable, because of its shielding and its hopefully geometric symmetry, if you choose the symmetrical cable design, which is 3 phases of conductors and 3 reduced size grounds, and I'll try to find a picture of that in a second. What do you get back for that 50% increase in the cable cost, which, by the way, turns out to be insignificant in the total installation, in the cost of the total installation? Well, at installation, you immediately get the benefit of a cable that is much more flexible. And if you've ever had to wrestle around with a 500 MCM cable with a low number of strands in it, just try trying to draw a rebar through your conduit. It's not a fun exercise. The fact is that the highly flexible inverter duty cable is because of the higher number of strands, which are done more to ameliorate noise through the Litz effect of a highly stranded cable and the increased surface area. But has the added benefit of being extremely flexible at installation, and therefore you will save some money at installation. The handling of this cable is just remarkably easy. Now, the other thing about inverter duty cable is that it reduces wear and tear on the motor insulation. And it also allows a, here, let me just put this up here. Good grief. I'm definitely having some significant navigation issues on my computer today. So this is the symmetrical ground VFD cable with the three small grounds as opposed to one big ground. What's the advantage of this? You get geometric symmetry between the conductors and better noise cancellation. So the benefits of spending 50% more on your cable: flexibility at installation, much reduced stress on the motor winding, and because this cable has less capacitance, you get two big benefits from that. You actually get less losses in the cable, because if you have high capacitance in your cable, you've got to push more voltage against that capacitance to get current flow. So the low capacitance makes you pick up minor, 0.1% efficiency on the system, but that again ends up being dollars over 10 years. The other thing that you get is a whole lot less capacitive coupling to ground, and that is a very important point, because the capacitive coupling to ground causes the ground plane to bounce. And when the ground plane bounces, everything that you've connected to the ground that depends on the ground to be zero in its software programming, such as pressure sensors, flow sensors, PLCs, all of a sudden it's like standing on a floor in an earthquake, and you're not quite stable, and your instrumentation systems and your control systems as a result are not stable, and you're going to get fault tripping. So capacitive coupling to ground causes the ground plane to bounce and causes the control systems to go nuts, which makes extra stress on you, which makes you drink more and increases the revenue to the alcohol store down the street. If you have ever had to deal with a capacitive coupling problem at the time of installation, you know why people drink. Costs go out the roof in trying to solve the problem. Craig and I had that pleasure of being together under the gun, and I think we collectively spent probably 40 hours or so, not to mention the electrical engineer and the electrical contractor, all the vendors that had to contribute. We finally got the problem solved, but we would have been much better off if we had used a better cable at installation. So, again, reviewing, we addressed the thermal issues with an innovative approach to installing VFDs, eliminating air conditioners. We're recommending that you use inverter duty cable. We are recommending that you eliminate the use of bypass. That's a strong statement, and I'm going to tell you right now so that the lawyers at Yaskawa don't flip out. That is my opinion. That is not Yaskawa's opinion. Craig can chime in on his own, but as far as I'm concerned, you do not need to use bypass. Now, bypass came about, and I remember it because I've been in this business longer than I care to admit. It came about back in the day when VFDs typically used to blow off the wall regularly, and customers wanted to try VFDs, but they said, I want a second parachute. And they put bypass systems around the VFD such that when the VFD lit up, they could bypass around and run the motor across the line. For the larger horsepower systems, we installed a soft start bypass. Therefore, I wouldn't have to start the motor across the line, but if the VFD blew up, I lost my speed variation capability, yet I was still able to run. And in those days, we still had the diverter valves and discharge valve, throttling valves, call them what you will, so we could still alter the output of the pump in the old mechanical way. Today, we're not installing throttling valves in bypass circuits anymore. So going to bypass means you're going to get the full output down the main line. No way to modulate it. But the main point, and the reason that I say bypass is not a good investment anymore, is that the bypass will increase the cost about 20%. And when you put a soft starter on it, you're going to increase the cost about 30%. Again, the theme of this discussion is how we can make better use of our money investing into these water flow and pressure control systems. And I'm stating that the 20 and 30% investment can be spent better elsewhere. Spend it on inverted duty cable. The bypass system actually has a far lower mean time between failure rating than the VFD itself. The VFD systems today are so reliable compared to when we implemented bypass back in the early 90s that it just numerically makes no sense whatsoever when you do the failure calculations. So if we're going by numbers, eliminate the bypass. Eliminate the soft start bypass, spend the money somewhere else. If you need an emotional backup because you're a little bit unsure, well, okay, you're going to spend some money to get that. And it's a kind of insurance. But my father used to say there's a reason why insurance companies all exist in really big fancy buildings. And it's because they make money reducing your emotional perception of risk. They know the real risk. And they don't insure something for less money than it costs to keep the thing running. They insure it for more. Bypass is that situation now. And it's mainly because the numerical, proven reliability performance of drives has increased so much, and I'll give you a quantitative estimate of that. Back in the day, drives were 30, 40,000 MTBF, mean time, 30, 40,000 hours mean time between failure. And when you take it, when you consider that there are 24,000 hours in a year, basically what we were saying is that back in the day, when we're talking the early 90s here, you install a bunch of drives and you're going to get a failure within 2-3 years. And indeed, that was the case. Today, the MTBFs on Yaskawa product, and I will leave you to ask that question to other vendors because I do not know their MTBFs by heart. But our MTBFs are, the actual MTBFs are in excess of 750,000 hours. Sorry, 750,000, so 750,000 hours. So we are 15 times more reliable than we were back in the day when we decided to use bypasses and specified them in. Bypass is a legacy. It exists on the specification because we didn't do the evaluations again, and if we had, we would say, oh, we need to take that off. So if we're basing our decision on a 40,000 hour variable frequency drive MTBF, well, I haven't seen a VFD that has that poor performance in almost 30 years. Therefore, the numbers dictate that we reinvest that money more effectively somewhere else. So I hope this has been helpful in a little bit of insight beyond the VFD itself. A couple things we can do to improve the application. Again, in review, the idea of using NEMA 3R enclosures indoors and using outdoor air to maintain them. The basic idea of getting rid of air conditioning, period, even in single outdoor applications. Certainly we've proven that, with lots of performance of our little white boxes on cement pads up and down the Central Valley. The use of inverter duty cable, a little bit of an investment to get a large return, and the elimination of bypass. There are several other design issues auxiliary to the VFD itself that we will comment on in future classes, but we're just about out of time now, so I'm going to say 2 minutes early, because I've run out of things to talk about, that it's 7:58. It's time to go to work, and we will see you next week on the Wednesday Yaskawa IQ training class.
Thank you.
Thank you, Pierce.